Hi, Janissa.
Good
A very
evening,
good
sir.
evening. How do you do, Janissa? Am
Fine,
I
sir.
audible?
Yes, sir.
Yes. Let me put off the fan. Maybe the fan is having some noise. I appreciate your punctuality. I'm very happy, Janissa, to spend time with you on chemistry. Let us move forward. We were at Henry's law, as we can see here. Yes. Yesterday, we were working on some problems related to molarity, modality, mole fraction, and mass percent, and those problems were well understood. These problems are very important, Janissa. You see, in-text questions. These in-text questions should be carefully looked into in each chapter. Wherever there are such, oh, in each chapter, where are such wherever there are such in-text questions, we have to write it down and answer the questions. That is very, very important because these questions quite often will appear in the question paper. Uh, Taken your dinner, Janissa?
Yes,
As
sir.
you, I could not hear.
Yes, sir. Can you
Good,
hear
good,
me now?
nice. As you concentrate more on preparing for your exams, there is greater stress on you. You should be concentrating on proper diet as well. The best timing will be, Janissa, as far as my experience is concerned, early morning time will be the best for preparation. And nowadays, we have phones. So even while laying down on our bed late in the night, we can browse through in our mobile phone the soft copy, e-version of the units that I have sent. You can just download them and browse through and study. Early morning, 4 to 8 is the best part of revision, best time for studying, so that, I somehow feel that, the length of the day, the length of the hour will be longer in that time, early morning. Time moves slowly. Of course, it's my experience. It may not be true for all. So please utilize that particular time for revision. Have these units in your mobile phone and try to read during the early morning. That will be very useful for revision. We'll try to advance as much as possible today and tomorrow, and day after tomorrow. I'm told that early in the morning you will be leaving to college. Uh, I wish to continue there too. You can say that I'm not a teacher, but you can say that I'm your relative, I'm your uncle, or something like that. You can say, and as a family friend, you introduce me, and that is how we can interact. Because it's not very advisable to have tuitions in the college. That is not advisable. So you can say that he is my relative, he is my uh, uncle, like that you can say, and that is how we can discuss important questions. Okay. I think we'll get opportunity even after you go back to your college until the 15th of February, because Janissa, in the initial time we have to go slowly, then we'll be faster with other units. Okay. So moving forward, we have understood how to calculate the molarity, mole fraction, mass percent. So now the important question is solubility. We know very well. Here comes the law, that is Henry's law. And Henry's law, as I explained you, the partial pressure of a gas is proportional to mole fraction of the solute. P is equal to KH into X, where KH is the Henry's constant. Using that, we can deduce from the given value of pressure how much of amount of solute is dissolved in a particular solution, or provided when we have the values of P and X, we can also calculate the value of K. KH is Henry's constant. Henry's constant deals with the solubility of a particular solute in a solvent in the preparation of solution, and the effect of pressure on the solubility. Okay, how the pressure influences. Greater the pressure, of course, the solubility will be greater. Using that fundamental principle, we will be calculating the amount of the dissolved gas in a solvent. Okay, let us see some examples and some practical applications of Henry's law. It may be asked like this: what is Henry's law and what is its practical importance? And a problem will also be asked, and it can be for 4 marks. This is a very important question. Okay. A problem based on Henry's law can be for 2 marks, and the question can be like this: the pressure, the partial pressure of the solute is uh, the partial pressure is value will be given, and the mole fraction of solute will be given, and we will be asked to calculate the K, Henry's law constant. Let us move forward in this. Let me verify one parameter. I'm just looking into the pressure conversion, atmospheric units of pressure to bar, and it's 1 atmosphere is equal to 1.013 bar, but still yeah, it's still in the steady material that is given, the value given is 0.98 bar. I want to understand the discrepancy. Okay. Ah, can you please read the bold text here, Janisa? Uh, the law from here. The law.
The law states that at constant temperature, that the solubility of a gas in liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution.
Absolutely. Okay. The solubility of a gas in a liquid. Here the solute is gas. Okay. We can also say the solubility of solute in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid. As you can see here, this is the weight, and the blue color is the gas or solute, and the gray color is the solvent. Once we increase the pressure, W1, W2, W3. When the partial pressure is increased by virtue of piston or something like that, what is happening? The volume of blue region is drastically decreasing. The density of the solute at the surface of liquid. This is the interface. This is the interface where the blue and gray regions join. That is what is called interface. What is happening is, upon application of pressure, the gaseous molecules are forced to dissolve at higher amounts, at higher concentrations in the liquid. That is what is called Henry's law. And you can see the plot like this. You know, when you plot concentration of gas versus the partial pressure of gas, you will get a linear plot passing through origin, because with the increase in concentration, the partial pressure of HCl and concentration of HCl vary linearly, and the slope of this plot gives the value of KH. Okay. It's simply, you see the mathematical equation y is equal to mx. Okay. Because the line goes through origin. If it intercepts at the y-axis, the equation will be different. Y is equal to mx plus c, where c is the y-intercept. Okay. But in this case, the line goes through origin and the slope. This is the slope. When you draw a straight line from any point on this line, vertically down, and also one horizontal line that meets this line. And the intersection of the horizontal and vertical lines gives, okay, here we can take, this is y2, this is y1, this is x2 and x1. y2 minus y1 by x2 minus x1 gives the slope. Okay, that slope is called the Henry's constant, KH. Okay, ma. P is partial pressure, X is the mole fraction of the solute. This is how we mathematically express the Henry's law. Moving forward, here you see beautiful examples of how does the KH, you see the K represented here is capital K, and you should never get confused with equilibrium constant. Okay, when we deal with Le Chatelier's principle, we often deal with chemical equilibria. Equilibrium is singular, equilibria is plural. For equilibrium also, we use the symbol capital K. What is equilibrium? Equilibrium is a condition of a chemical system where the rate of forward reaction is exactly equal to the rate of forward reaction, and we may tend to think that the reaction has come to a standstill. But it's not true. In reality, it's not true. The reaction has not come to a standstill. Rather, it's dynamic. Okay, because the forward reaction and the backward reaction are happening at the same rate. There is no perceptible change in the equilibrium constant. That is what is called equilibrium means. Under the condition of chemical equilibrium, the rate of forward reaction as well as the rate of backward reaction will be equal, and that is what is called the condition of dynamic equilibrium. And equilibrium can also be represented with capital K, but here capital K does not represent equilibrium constant, rather it is Henry's constant. Emma, you can see in this table, we have different gases like helium, hydrogen, nitrogen, oxygen. As you can see here on other column, we have temperature. What is happening? Let us take this example. When nitrogen is present at two different temperatures, one at 293 and 303, we know very well with increase in temperature, the solubility should decrease. Okay, because there is always something called fugacity. Fugacity is nothing but the escaping tendency of some chemical species. When we heat a solution, dissolved aqueous solution with dissolved gases, when the temperature is increased, what will happen is the gas will be evolved, removed. Okay, so the solubility, the solute that is present in the liquid solvent is lowered. So with increase in temperature, what do we expect? We expect decrease in solubility. Okay, that is reflected in terms of increase in KH. You see the KH value increased from 76 to 88, nearly 12 units of increase. Likewise for oxygen also, when the temperature is increased from 293 to 303 Kelvin, there is no much change in the temperature, nearly 7 plus 3, 10 degrees centigrade. You see, whenever we talk of 10 degrees centigrade, the Arrhenius law comes to our mind. What does the Arrhenius law says? Arrhenius law says that for every 10 degree rise in temperature, the reaction rate is dash, double. Emma? So the reaction rate will become double. For example, at 30 degrees centigrade, per se, a particular hydrolysis reaction has an activation energy of 30 kilojoule per mole. When I increase the temperature from 30 to 40 degrees centigrade, the 30 kilojoule per mole, for every 10 degree rise in temperature, the reaction rate is doubled. Means the activation energy, what will happen? It will be lowered. Okay, 30 kilojoule per mole will be reduced to per se 28 kilojoule per mole. Rate increase means activation energy gets decreased. That is the way how temperature has an effect on reaction rates and activation energy. We'll come back to Arrhenius law when we deal with chemical kinetics, and let us come back to the Henry's law. Henry's law constant Hk is a function of okay, pressure and concentration, and the concentration of solute is in terms of mole fraction. And you can see here with increase in temperature, what is happening is the KH increases. The KH increases because you see P is equal to KH X. Okay. With increase in temperature, what will happen is X will decrease. When X decreases, KH will obviously increase because X appears here in the denominator form. Apart from nitrogen and oxygen, you see, the unit of KH is kilobar. Okay, X is the mole fraction. Janisa, please remember, mole fraction is fraction. Whenever you say fraction, it is a ratio. It doesn't have any units. We know very well mole fraction of glucose in glucose solution is moles of glucose divided by moles of glucose plus moles of water. So, okay, numerator will have the same unit as that of the denominator. So the units get cancelled. Whenever we say fraction, it's a unitless parameter. So KH will have obviously the units of pressure units, that is bar or kilobar. Okay. That is how Henry's law is defined, and KH is defined. And you please see this particular problem, Janisa. Such problems, are very important, and quite often such problems appear for 1 mark questions. Janisa, would you mind reading for me the caption of this problem, example 1.4?
If N2 gas is bubbled through water at 293 Kelvin, how many millimoles of N2 gas will dissolve in 1 liter of water? Assume that N2 exerts a partial pressure of 0.987 bar, given that Henry's law constant for N2 at 293 Kelvin is 76.48 kilobar.
Absolutely. So we know Henry's equation. Henry's equation is P is equal to KH into X. We know here P, we know here KH. What we want to know is millimoles of N2 gas. Millimoles of N2 gas. That is basically the concentration. X we wanted to find. So let us write down the equation. P is equal to KH into X, and then X becomes, X means concentration of nitrogen. Okay, mole fraction of nitrogen. Okay, from mole fraction we can always calculate the moles. Okay, mole fraction of nitrogen is equal to partial pressure of nitrogen by KH. Here if you see, the partial pressure of nitrogen is given as a 0.987 bar. 0.987 bar divided by KH value is also given. What is the KH value that is given? Henry's law constant is 76.48 kilobar. See, Janisa, here what is missing? 76.480 bar. Okay, but what is given? Kilobar. What is missing is 10 power 3 is missing. Here there should be 10 power 3. The 10 power 3 in denominator, when it comes up, it will be 10 power minus 3. Here in this problem, 10 power minus 3 in the numerator is missing. Okay, when we divide 0.987 divided by 76.480, what will we get is 1.29 into 10 power minus 2. Already there is 10 power minus 3, 10 power minus 2 and minus 3 multiplied together 10 power minus 5. So this is the mole fraction of nitrogen. From the mole fraction of nitrogen, we will calculate the moles of nitrogen. What is the solvent here? 1 liter of water. Okay. So again, mole fraction of nitrogen is equal to moles of nitrogen by moles of nitrogen plus moles of water. Okay. 1 liter of water contains how many moles? Moles is equal to weight by molecular weight. What is the weight of water? 1000 grams divided by 18 grams. 1000 by 18 is equal to 55.5. Okay. 1 liter of water contains 1 liter of water contains, okay, moles. Moles is equal to weight by molecular weight. 55.55 moles. Am I correct? So moles of nitrogen is mole fraction of nitrogen is equal to moles of nitrogen by moles of nitrogen plus water. Here, one more important thing that you should take into consideration is that the solvent water is present in large excess. So ideally, this can be neglected. 55.5 can be neglected, and in the denominator is neglected as number of moles of nitrogen is far, far lower than okay, n is neglected because the amount of nitrogen is very small compared to the water. So number of moles is equal to n by 55.5. Agreed. And we have number of moles of nitrogen that is calculated is 1.29 into 10 power minus 5. So n by 55.5 is equal to this much. So how many moles of nitrogen are present? N is equal to 1.25 into 10 power minus 5 into 55.5 moles. So we have 7.16 into 10 power minus 4, or it can also be told as 0.716 millimoles. Agreed, Amma? Any questions? No questions. Here, what you have to carefully see is P is in bar. So KH also should be converted to bar. 10 power minus 3 is missing here. One more thing is that here, while calculating the mole fraction of nitrogen, n mole should be neglected so that the calculation will be easier, because you know the in the denominator the solute that is present, the nitrogen that is dissolved in water is too low compared to the water actually that is present. In such cases, you know, we can neglect the n. It makes no error. So basically the moles of nitrogen becomes equal to moles of nitrogen by water, and then mole fraction of nitrogen. This is the mole fraction. Becomes moles of nitrogen by moles of water, and then the moles of nitrogen is this much, and to get the millimoles, what do? We divide it by 1000. Okay, into yeah, 1 mole is equal to how many millimoles? 1000 millimoles. 1000 millimoles. So we have to multiply, replace moles with 1000 millimoles. That is how you calculate the millimoles. Because the question, you see, the basic question is to express, to find out the millimoles of nitrogen of solute that is present in 1 liter of water. This is one of the questions that is based on Henry's law. So you should never forget Henry's law. Okay, ma? Henry's law is equal to P is equal to KH into X. It should be imprinted in your mind. This is just revision, you know all these things. Okay. In the question, you may be asked what are the practical applications of Henry's law? Okay. Henry's law find several applications in industry and explain some biological phenomena. For example, in deep diving, that is what is called a scuba. Scuba means self-contained underwater breathing apparatus. We know divers, people that dive under the oceanic water. They carry, their own gas cylinder for breathing, and it has a typical composition of air, but under compressed conditions. So there will be, when they breathe the air under such pressure much higher than atmospheric pressure. Much of the nitrogen goes into their bloodstreams, and there will be nitrogen bubbles that are formed, and that situation becomes more dangerous the moment when the divers come out, and there will be bubble formation in the bloodstream, and it gives to a health complication called as binds, and it is detrimental to life itself. So to avoid such conditions, because what do we mean here is Henry's law states that under such high pressure, the amount of nitrogen that is dissolved in the blood, here the solvent is blood, solute is nitrogen. Based on Henry's law, we know practically because of the high pressures in the cylinder, more of nitrogen is going into the bloodstream and causing a severe health condition called pints. To overcome the problem, what we do here practically is dilute the air in the cylinder with some 11% helium, 11.7% helium, 56.2% nitrogen, and 32.1% oxygen, so that helium will not form bubbles, and the excuse me. Usually, Janissa, by God's grace, I give lectures for hours. I will not get tired. It's only God's grace. Non-stop. I never drink water as well. It's very rare. Okay. Uh, it's the grace of Jesus Christ. Moving forward, Janissa, not only under underwater conditions, even under air, high altitudes also, there
Sir,
are some conditions like
sir,
low amount of oxygen
sir,
availability.
sir,
Ah,
sir,
ah,
I'll go drink water and come, sir.
please, please. No hurry. Yeah, you can. Yes. Nine or 96. P 96.63. There are some typing mistakes like this that we need to take care. Okay. Delta TB is equal to Kb into molality. Molality is number of moles of solute in 1,000 grams of solvent. Yeah, this is the solute. This is the solvent. This is the equation delta TB, elevation in boiling point, temperature difference, and Kb into M. Okay, good. Such problems are very important based on the colligative properties. This is what I was telling. Problems based on colligative properties. Yeah, let us move back. Hope you are able to see the screen. Okay, now there is another problem here that is based on Henry's law. Can you please read the example 1.6, Janisa?
H2S, a toxic gas with rotten egg-like smell, is used for qualitative analysis. If the solubility of H2S in water at STP is 0.195 m, calculate Henry's law constant.
Absolutely. What we have to calculate is KH. Okay. We know very well the unit of KH is bar, kilobar or bar. Okay. We know the pressure. This is very important, at the standard temperature and pressure. What is standard temperature and pressure? Standard temperature and pressure means the pressure of 1 atmosphere and temperature, room temperature. Uh, but usually here, I told you Henry's law constant is expressed in terms of bar. So we should able to convert atmosphere to bar and it will be 0.98 or something. Your teacher has fortunately given you this answer. As you can see here, that made our life easier. Yeah, the solution is here and it is perfect. Okay, this is the equation. pH is equal to Kx. This is the fundamental equation for Henry's law. You see pH2, partial pressure of H2S, hydrogen sulfide is equal to KH into XH2. The pressure is not given. Okay, ma. When we see the term STP, standard temperature and pressure, we should understand that the pressure is 0.987, okay, bar. 0.987 bar, because 1 atmosphere is equal to 0.987 bar. This is how we have to convert the pressure units. STP means 0.987 bar. How to calculate the mole fraction of H2S? Mole fraction of H2S is equal to moles of H2S divided by moles of H2S plus moles of water. And what is given here is solubility of H2S in molality 0.195 m. Okay. From what does the molality says? Moles of solute in 1,000 grams of solvent. Okay. So solubility of H2S in water. From the term of molality, we know that the number of moles of H2S is 0.195. When we take 0.195 as the number of moles of H2S, here N H2S divided by NH2S plus NH2O. Please use the second link, Amma. I sent you the second link also that starts from 10:50. In 10 more minutes, you can click on the second link and use the username and password. And from 9:50, we'll go for another 40 minutes. It will be slowly increased like that. Usually, Janissa, my lecture minimum goes for 3 hours or so. I do not want to exhaust you in the beginning, so I started with very small lecture hour, like 40 minutes. Moreover, I'm constrained by this Zoom. In Zoom, we cannot have a lecture for more than 40 minutes. There will be automatically a break. Unlike Google and Google, we do not have the access for recording. Okay, moving forward, number of moles of H2S divided by number of moles of H2S plus water, and number of moles of H2S, we know 0.195 divided by number of moles of water in 1,000 grams is 55.55. So this is the mole fraction. We got the mole fraction. As I told you, mole fraction will not have any unit because fraction, it's a ratio. Number of moles will have 1 unit, and the bottom also number of moles, it will get cancelled, and mole fraction or ratios will not have any unit. So KH, Henry's law constant, will basically have the unit of pressure. So KH is equal to partial pressure of H2S, that is already given by mole fraction of H2S. 0.0035 gives 282 bar. Janisa, can you please calculate for me this calculation? Because we cannot trust the calculations part. We have to do all the calculations by ourselves and ensure that the calculations are correct. There can be errors also. Please make this revision for me. 0.987 divided by 0.0035. How much? Basically, it is 1,000 divided by 3.5. Okay. 1,000 divided by 4 is 250. 1,000 divided by 3.5 is, naturally, it is around 282. Correct. Okay. But, there should be a space. 282 bar should be written like this. 282 space bar. Because, 282 is numerical value, and bar is the unit of pressure. So there should be a space. Okay. Moving forward, I'll save this so that the corrected version, I can send it to you. Yeah. Let us move here. There is another problem that is, based on Henry's law. We'll come back to it. This is basically the